Welcome to Homework Lib.
For this astrophysically based problem, it seems a little grandiose, but it's actually going to be using the same stuff that the rest of the chapter uses. So there's a long preamble, which I recommend you read, but essentially the question itself is asking us to take the data presented in an example previously in the chapter to calculate the energy and wavelength of a photon emitted by a carbon monoxide molecule in a rotational transition from the L equals 1 to the L equals 0 state. So that means we're going to be calculating a delta energy from the E1 to the E0 state, but E0 is just 0, so we can solve for E1. We get 1 times 1 plus 1, which is 2. The 2's cancel, so it's just h bar squared over the moment of inertia, which I've hastily scribbled over here, but it's also in the text. You can go and find it there. The calculation for the energy is then pretty simple because, again, we're given it. And in joules, it is 7.67 times 10 to the minus 23rd power. So not a lot of energy indeed. And to calculate the wavelength, we use the famous equation for the energy of a photon, flip things around a little bit to get this, and turning the crank on it, you see that you have a photon of 2.59 millimeters. So really quite a large wavelength, and this is this is millimeter wavelength, which is in the radio wave spectrum. Part B, though, well, here, we will box this to show that we have solved part A. Part B, on the other hand, wants us to think a little bit about the fact that these gas clouds are extremely cold. So around 20 Kelvin. But we've seen before that if a molecule in a certain gas has enough energy to put it above one of these rotational levels, then it's likely that you will find some of, or quite a bit of that molecule in those rotational levels. But since the temperature is so cold, we, you know, it doesn't make sense that we find so many carbon monoxides in this rotational state. But you'll see that it actually does make sense, because if you calculate the energy, just the rough energy for a given temperature, so Boltzmann constant times T, you get that it's 2.76 times 10 to the 20 minus 22 power, 22nd power. So it's this many joules. If you do a ratio of these two, I'll write it as delta E. So if we do KT over delta E, you see that it is 3 times, roughly 3.6 times higher. So the particles, even at 20 Kelvin, are still 3 times higher than that extremely low energy rotational band, which is also explained by these extremely low energy photons of millimeter wavelength. So That's why it makes sense that astronomers can detect radiation from carbon monoxide in these molecular clouds.